Hi everyone, this is coming to you from Education for All. This is our second video in looking at the completeness axiom. That's real numbers completeness property. This is a property of real numbers. Completeness is a property of real numbers because when you look at other numbers that we have, they are not complete. They have gaps in them. We have covered that topic earlier on, but along the way, we will give examples to explain that. There are some numbers like the irrational numbers. They have gaps in them, so they are not that very useful. They are important, but more or less, mathematicians don't like to work with them. Mathematicians, the model scenarios. They look at situation, then they model it, they will predict that situation, how it's gonna be in 2 years' time, in 5 years' time, something like that. So they like real numbers, not irrational numbers, because this concept of real numbers is trying to differentiate numbers between the real ones and the irrational ones. The real numbers are complete, while the irrational numbers are not complete. They have gap. There's a gap between them, amongst them. So what is an axiom? An axiom is something like an accepted idea in mathematical terms. It's an idea that people accept to be true. For example, they ask you 2 plus 2 is 4. There is no point for you to prove 2 plus 2 is 4. We'll accept it. 1 times 1, we know is 1. What are you going to prove there? So this idea that you don't require a proof to state something, that something is an axiom. You have other things like a theory. If it's not an axiom, then you have theory, or not even a theory before you go to a theory, or a theorem, right? It's something that has already been proven. You have facts to prove it. It becomes a theorem or a theory. We also have corollary. That is, if you say this is it, it implies that this is also this. So if the axiom is this, then it implies this is this. We have that. So these are all terms they use. So now, every non-empty set, forgotten set here. Every non-empty set of real numbers that is bounded above has a least upper bound called supremum. Yeah, this is the axiom. In every set that is bounded above, that set must have a supremum. That is what this axiom is saying. So before we go to the corollary, that is, if this axiom says this, then this is also correct. Every non-empty subset of real numbers, this R is the symbol for real numbers, that is bounded below, this time now below, has a greatest lower bound called infimum in real numbers. So when we say completeness axiom, these are the two things you really need to know. These two definitions, if you like. You need to know them. And in due time, we shall explain the applications and importance of this completeness axiom in due time as we go along. As I stated earlier on, we want to start from the basics, the elementary stuff. This is the very elementary stuff when you are doing real analysis. The higher you go, the more you go, the more you meet difficult stuff. You'll never meet easy stuff again. You see? So that's why it's best to start from scratch. So let's look at this definition again. Every non-empty subset, I can call it subset even instead of set. Every non-empty subset of real numbers that is bounded above has a least upper bound called supremum. So now let's look at this set here we have, set S. Is that X is in the real numbers, such that X squared is less than 2. Now the question is this set bounded above? When we explain why we use real numbers, then you will actually be convinced that this is indeed a very important. Let me just make this thing to be very important topic. Shall explain that as we go along. This is a set wherein all the squares, which are the numbers, the square of numbers that are less than 2. That's what they are saying. The square, you already know root 2, for example. If you punch this in your calculator, you'll get 1.414278614 something like that. 5. You'll get these numbers. It just depends to how many digits your calculator can display. Some calculators, they display like 6 digits, stop here. Some display up to here. Some powerful computers, they give more. So the square root of 2 is actually, it keeps going. It doesn't stop. It just depends on how far your computer can handle these numbers after the decimal point. So now here they ask you whether this set is bounded above. It's bounded above. That is, we already explained what it means when a set is bounded above. Yeah, the highest number in the set, or the highest element in the set that is also included in the set. So yes, it is bounded above. And what is the value is root 2. Why? Because root 2 is in the real numbers. The set has a supremum. Therefore, the set has a supremum because it is bounded above. The question was, does this set have a supremum? That was the question I should have asked. Right? Now compare this set and this set. What is different between them? What's the difference? What difference can you spot? This is in real numbers, R, and this is in rational numbers. So there is an element in the real numbers. This is an element in the rational numbers. Such that that element squared is less than 2. Now, the question they posed here is, does this set have a supremum? Does it have a supremum? This set here you are looking at, does it have a supremum? This one. What is the difference? This is real numbers. This is just to emphasize the point that real numbers do not have gaps. They cover everything on the number line, while rational numbers, they do have gaps. They do have gaps. There's a hole in them. So if you are, for example, you are driving and using sat nav, yeah, satellite navigation system in your car, and those numbers there, because it's numbers they use there to calculate the road, to direct you where to go, it's real numbers they use at the background of that screen. You see the program at the background is real numbers. If they were using rational numbers, there will be gaps. So what would happen when you reach where there is a bridge? It doesn't show that bridge because that number is not there. So you jump inside the bridge or in a gutter or somewhere else. It could be catastrophic. So that is why mathematicians, engineers, scientists, they like using real numbers instead of rational numbers. This is just one aspect of it I mentioned. We shall talk about that when we delve deeper into this topic. So yes, although this is the highest number here, or it is bounded here, but when you look at rational numbers, root 2 is not a rational number. We have done that proof. Root 2 is an irrational number. So root 2 doesn't exist in this set. This set is talking about rational numbers. But root 2, you cannot express root 2 as a fraction of integers. That's what it means. This is root 2. This is root 2. You cannot express root 2 like 1 all over 5 or 6 all over 11. You cannot do that with root 2. All these square root, cube root things, you can't, it's impossible to do that. So because you cannot express it as a fraction of integers, so this root 2 is not a rational number. And this set is talking about rational number. So this number does not belong there. Therefore, within the rational numbers, T has no rational supremum. There is no supremum because root 2 is irrational. Thus, Q is not complete. So this is not complete. Right? As I said earlier on, this topic is very, very abstract. And the one we shall move to after this one, which is the proper definition of a limit, where we are going to use the epsilon delta definition of a limit, more abstract than this. It's more abstract than this one. So as we start to solve problems here, then you shall understand better as we go along. Thank you for watching. Yeah, bye bye.